Okay. So, do you see my screen?
Yes.
Okay, that's perfect. So the only two feedbacks I've got from previous lectures was lack of formulas and willingness to learn English better. That's why I decided to make a lone self-explanatory variables name in the code. That's it. The rest we will focus more on a high-level logic and understanding why this is why this works and how can it be adjusted. And as we have pretty small audience today, we will have time to discuss all concepts in details, go through your questions, and so on. So topic of this meeting are recommenders, and let's start from what actually recommenders are. The simplest thing to understand it is to go on Netflix and see what they are recommending. So they just try to offer you something extra. Or to go to Rosetta and you will see something extra that they try to sell, basically replacement of toaster, which I was viewing in that moment, or extra products that customer might want to buy. If we will try to formalize it, we can say that we have an assortment, and in certain circumstances we want to propose extra item to a customer. If we go further with formalization, our algorithm would have an input as user ID and metadata about circumstances where we need to sort our assortment, and in a certain way select an items from that assortment. And if we go further and look from a business perspective on this process, we'll find that there is several key things what we can try to achieve. So, first of all, we might try to sell extra item. That's clear. Rosetta try to sell extra component to our kitchen in the screen above. We might want to offer alternative, the same we saw on the screens above, and we want to keep customer active. Basically, if you used to scroll Instagram, well, that's it. So they try to maximize time you spend scrolling. So that's also one kind of recommender system. And again, if we go to formalization of these goals, we'll find that all three are about money. But first, we can estimate as amount of money we'll get per each view of recommendations we give. Second, we can estimate by amount of time or clicks that customer do on our platform. And third thing is a bit tricky, is how customer addictive to our platform and how often he return back to us. And if we try to write a formulas, we will end with this funnel. So basically, not formulas exactly. So we have view of our recommendations. We have certain feedback that we get from it. It's click or any other action, and we have value of this feedback. For example, on e-commerce, you will see that there is long funnel of purchase, processing, refunds, etc. We aggregate it and say that this is single value. Retention rate usually is not used in optimization of algorithms just because it's computed on a horizon of 6 months. We keep that in mind, but usually we estimate it, just keep an eye on it, but not incorporate as a part of our funnel. So let's also give a look on data that we can expect when we building our recommender. Pretty common situation when we have users and some information about them. We have items we want to recommend, and they also have certain attributes. We have their interactions that consist explicit and implicit feedbacks, and we have certain logs about our recommender system. good practice is to build a recommender system based only on interactions, ignoring logs, because usually they are pretty noisy. And a bit later, we will see how system bias itself. And also, we need to talk about feedbacks. As I mentioned, there are two types of feedbacks, though they are explicit and implicit. Explicit is when you are directly asked to give it. So when you give amount of stars to a certain movie, or when you press finger up or finger down on a to rate quality of movie for you. And implicit is something that is computed based on your actions. For example, if you go to a page, we can assume that you're interested there. If you watch movie for 30% of movie, perhaps you like it. That's how it works. But there are a lot of specific about those ratings, and I think we need to go there before actually we understand why algorithms work in one or another way. First of all data is sparse. So we work with matrices, and when we work with implicit feedbacks, we have really small amount of data. When we ask customers to rate, we have even less data because because not all customers rate what they watch and give us feedback about their experience. Just to visualize what sparsity is, we can write a matrix, kind of matrix. Let me adjust it, straight lines. 1, 2. Here we have users. Here we have items. And level of sparsity is the amount of cells that are filled here. So basically, metrics of interaction of customers are usually mostly empty. Any questions? No? Okay, perhaps some noise outside. So, second property of these ratings is bias. And well, for implicit, we have. Sorry? Did anyone ask anything? No? Okay. Feel free to interrupt me. As I mentioned, audience is pretty narrowed down, so we can discuss everything in real time. So, when I work with implicit feedbacks with this, we have popularity bias, because you might see that when you come to a certain web shop, you click on popular items, and they attract more and more views. But in the same time, we have explicit feedback, and it could be biased by any circumstances. For example, it was proven that people tend to rate higher something if they see a random number that is on a certain level. It was checked on random questions like what is amount of, for example, articles in Constitution of Nicaragua. Okay, I mean, not everyone knows that. And on a backlog, there was emulation of a lottery with random numbers. It was proven that people give higher values, higher responses when they see higher numbers from that random lottery. Also, we might expect that customers tend to follow the crowd and not to give low rates if average rate is high. Also, you will never go to give feedback, almost never, to give feedback for when something is okay but not extreme. Usually people give rates for when it's too good or too bad, just to share their feedback when they think it's value. So it's pretty biased. And also, there is a high risk of manipulation for explicit feedback when people try to promote their favorite book author, or perhaps someone tries to, on a marketplace, get better position in a search. So when you work with explicit rate, you will need to deal with a lot of biases, and you need a lot of normalization. For implicit less common, it's easier to filter because if our platform require authorization, well, mostly it would work. But with implicit feedback, it's pretty noisy because well, let's be honest, we click everywhere where we go on a website, and if we rate each of these that clicks as a strong signal, well, the system would fail. So we need extra filtering there. Another thing, if we want to use a negative feedback for explicit situation, you would get it. So you even if you have stars from 0 to 10, you might set a certain boundary where you say that it is good, where it is average, it is bad. With implicit feedbacks, it's not possible. So we need to take that into account. And one of the worst thing about recommender system, that it's pretty often we can experience a feedback loop. Why? Our recommender system gives something to customer, and customer interact with these products, and we get feedbacks only about those products. We use the data to train our recommender system, and again we have information only about those products, and so on, so on. So, do you have any questions about this part?
У мене коротеньке питання стосовно фідбек-луп. Тобто, якщо клієнт дуже мало подивився продуктів, вибрав щось одне, і типу йому будуть рекомендаційна система може зайти в цей луп і пропонувати йому тільки один тип товарів, більше нічого, типу в цьому полягає вона?
Ні, не для одного кастомера. Якщо ми подивимося на рекомендації, які дають різні, ну, наприклад, Netflix, в них є трендінг. Тобто, що люди дивляться зараз? Чи US Movies, але вони ранжуються також по що люди дивляться. І дуже складно, якщо люди дивляться одне і те саме, і ви рекомендуєте на основі того ж цих переглядів включити щось нове сюди. Тобто в нас є лімітований список, які ми рекомендуємо, і дані з переглядів якого ми використовуємо для наступних ітерацій.
Розумію.
Тобто ми направляємо користувачів туди на популярні айтеми, та вони популярні, тому що ми багато кастомерів туди направляємо. Тому алгоритми часто biased просто по дизайну, як кажуть.
Зрозумів, дякую.
Інші питання? Добре. Давайте подивимось на найбільш популярні алгоритми, які є. І потім трошки подивимось на реалізацію їх у коді. So, the most popular thing might sound like pretty strict and stupid, and that is recommendation about popularity. If you think that there is no machine learning, just try to look on it from practical side. So you have not only, so these are basic formulas, nothing, no rocket science. But imagine a situation that you need to estimate rates or conversion rate, for example, for items with low amount of data. Most probably you will come to a certain statistical distributions, and in a case, for example, of e-commerce, that would be better binomial distribution, so a process that improves itself. If you want to rate it more complex, to make your life more complex, think about different margin and different effect of each of those products. If that's not enough, think that those values could dynamically be changed. For example, if your team like to give discounts. So basically, you need to every time retrain model and estimate those dynamically and pretty fast. But main idea of these most popular items is that you always can recommend that. Even if you don't have information about customer, you can say that, okay, let's show him something. And that's pretty valuable because recommender systems by design are big and you can't retrain them in real time. You usually retrain it once per day. So you have this luck where you still want to show something. Yep. So small remark. I don't see if you raise your hands. I just do not on that tab. So Dmitra, may I ask you to interrupt me if someone wants to say anything? Or if we still have a small audience, just feel free to interrupt me. Yeah. So and let's continue. And this is a base algorithm that usually used as a backup of anything you would like to build. The second section of algorithm is filtering algorithms. They are much more advanced, I would say in this way, but at the same time they use pretty similar idea. So we compute average rate as sum of all rates divided by n customers. We compute rate for collaborative or content filtering, whereas weighted rate divided by, and that's it. Core difference of this algorithm that we have a matrix of similarities between items or between users. Okay, sorry, I went too broad. Let me tell first actually how does it look like. So we have filtering algorithms and we can classify in two ways. First of all, by data that we use. It might be collaborative when we use data about interaction of customers and products. And it might be content-based when we use attributes of products or attributes of users. And also we can set similarities in two different ways. We can take similar users and say that they show us if users are similar, that we expect the same behavior and we can recommend what other users enjoy. And item-based, where we say that, okay, if our customer interact with a certain set of products, we recommend a similar set of products and he should be happy. And the core concept of all this is a matrix of similarities. It looks pretty simple. For example, we have, for example, for items, we have items here, item here. We have item G. And we want to, in certain way, get how similar they are. We can say that this similarity might be computed based on, for example, attributes. It will be one if, for example, country E equal to country G, and 0 otherwise. Or it might be more complex when you take information about customers, where your item E is a vector of customer interactions, rate of set of customers. Okay, let me draw this right, it would be better. Where are my lines? So we have a vector, we have item first, item second, and we have all customers here. Customer, okay. And we encode the information with ratings or, for example, numbers. Like 0, 1, 0, 1. And we want to compute how similar they are. So we can say that this interaction is a vector that represents product. Take a vector cosine between those, and we'll get a certain figure that show how similar they are. So basically, another rating would be as a cosine of rates A, rates D. And so on. So a core idea that you, in a certain way, say what is similar items and train your system based on it. It's pretty efficient method, especially if you overcomplicate your system. What we did on practice, we say that each our customer are represented by a set of products. So interact with. Then we say that we take all products that we want to recommend is similar to products he interact with. Like this. And then we aggregate ratings and basically based on those similarities and say that, okay, and then we select top n items based on this rating. This adds enough flexibility to the system and could be adjusted to almost any situation. The most popular similarities that we use were based on a cosine comparison, so based on collaborative filtering. Works pretty good when you convert text to embeddings and take the sign between those. Well, basically anything else you could imagine. For example, we try image similarity. Well, it works. When you compare distribution of colors between different products. Okay, and third one, the biggest thing is matrix decomposition technique. Basically, idea of matrix decomposition is pretty simple. We have sparse matrix, and that takes a lot of space. We say that each cell could be represented as a multiplication of vector of certain user and with vector for items. And there are two approaches to do that. So standard one is single value decomposition. And what it does, it comes from, well, first of all, it is precise method. So you take matrix, and this method tells you that you can precisely decompose to three matrices. One will represent users, one will represent items, and one with diagonal elements will represent a weight of certain factors. The problem with this precise method is that it works with it doesn't work with sparse matrices. So you need to fill empty cells, and then it would work. Unfortunately, on practice, that means that you need to put the average values, and you need to store that huge matrix that you will get. For most situations, it's not possible. The second one, altering least squares, take us to a bit approximate domain approximation, and idea of it is again straight and simple. We have two matrices, users and factors. So let it be users. How to say? Okay, let me do users from it. So we have factors and we have items. Okay, and we want to find their multiplication. Basically, as we already defined, it looks like this. But we can, if we want to approximate it, we can say that on each stage we say that one matrix is constant. Then we solve it as a system of linear system, as linear acquisition. So v equal m. From it we find values for v. And then on the second step we say that v is constant, and we find another matrix. And then we repeat several times this cycle. And we get approximate, each iteration will bring us closer and closer to real values. This method is much more flexible. You can parallelize because there are a lot of theory of solving linear systems, standard packages. Also, it's much easier to work with sparse information and with big amount of data. So personally, I advise to, if you will look for something from matrix decomposition, to use these matrices, this method. And so these are three main methods of how people usually build recommender system. Generally, the rest is just adjustment of what of these methods, and we'll look a bit further how does it work. For now, do you have any questions about these things? Okay, no questions. That's good. Oh, well. Let me switch a bit to code, and so I can show how does it look like on practice. Stop sharing and. Okay, so let's look on these three methods on practice. For this demonstration, I took pretty standard data set of book recommendations. This is how it looked like. Information about books. Most is not corrupted, even some images available. We have information, books information about ratings. Information about ratings, we combine both implicit and explicit part, so we can filter or combine those. The matrix itself is pretty sparse, so we have less than 1/100% filled entities. What else? Yeah, about customers, we have also some information about location and age. From location, I take only country for further processing. We'll use it a bit below. As to evaluate this system, I propose to use a method that is based on weighted, how to say. So basically, idea is of this method is pretty straight. We have certain list of recommendations, and so we know that customers interact with some of those. For example, they interact with this, they interact with that, and then they interact with the last one. And we say that our algorithm works good when it put items that customer interacted with from our test data set. We try to predict as high as possible. So for it to, and of course, as we have rated data, we should rate it differently. So we say that if customer put rating above 8, then we rate it as 1. If it put rate below 8, we rate it as minus 0.02. If it just interact with it, we rate it as 0.2. Don't look for a sense of these specific values. They're random, just from my head. So it's just to go from just to combine explicit and implicit feedbacks and be able to rate the whole data set. And yeah, I go through all customers in a data set and say and rate them separately, and then take an average score. No rocket science. A bit more interesting is how we can organize a split to a test and train sample. In this specific data set, it's not important, but on practice, most of systems you will design would need to predict future. Not even in time series, but when you train recommender on a data, this data is always from the past. It will work in the future, so you need to foresee it in a certain sense. That's why I decided to split dataset based on index. So for each customer, I take a threshold to say that before this threshold, everything is trained dataset. After it, it is test dataset. It is randomized, and well, I built it in a way that it gives approximately 30% of in a test sample. Before we'll go to recommenders, do you have any questions about this these adjustments I did to Common Logic? No? Okay, let's move forward. As I mentioned, any strategy is bad and has certain blind spots. First, the first strategy I decided to define here is backup strategy that will fill everything, basically based on popularity. No, again, pretty simple. As we already discussed, it's average rating, a bit it has a bit skewed to the left because to ignore items with a small amount of rating. So basically, if there is only few feedbacks, then we will see that rate will go down. It can be done using statistics, or it could be done just by faking and assuming that there are at least 50 people that give zero feedback, and if the rest gave significant enough, then we will score it better. And two tests for each that I did for each algorithm. First of all, the value on our test data set, pretty small, but we'll see that not the worst. And the response time, what is for backup strategy is mandatory because you need to put it on every strategy you run. So 100 nanoseconds, that's pretty good to have. Next one, basically it's again a backup strategy that based on similar customers. So that's already user-based collaborative filtering. Yeah, content filtering. How it is organized. We get a user ID. We say that he has a certain country, which we take. We take all customers, and if country is the same, we give them higher weights, actually 50 times higher than for the rest. It's done for cases when we have countries with pretty small amount of customers, so we want to be able still to get enough while sampling later. We say that we want to recommend customers for customer based on another activity of customers of roughly the same age, what sounds logical, and filter all those where we don't have ages. And everything we do is just, after computing weights, it's just sample thousands of customers from our data set, take books they rated, and again compute the same average rating. Based on it, we can sort and take the top 100 recommendations. Doing the similar steps, we will see that this decrease our quality of our recommendations. This is, by the way, this is pretty interesting data set where using of each next recommendation method more precise and better will decrease the quality. So that's not common, but it's important to know that that's also possible. And of course, we need to measure time. Significant rise of time, and this is what we observe. Do you have any questions about these two methods? No? Okay, let's move forward. Okay, next one is method is collaborative filtering. Yeah, no, okay, randomized. The interesting thing about collaborative filtering that it's pretty easy to organize in a scale way. So we can build it in a as a matrices organized, but then we need to store all those matrices. For this specific scenario, I usually prefer to use SQL type of instructions with joins, and it works pretty good. But to build it on practice, you can't really build it for all assortment because that wouldn't fit machine. And honestly, you don't really want to compute ratings of or predictions for items that are not often in use. That's why first thing I do, I filter respond by top 1,000 of books. Then I do a bit tricky thing. If you look on a cosine between vectors, imagine you have two vectors. Just to remind you, cosine is so when you compute a cosine, you first of all you take a scalar multiplication of these two vectors. So let it be. This will be this is. And then you divide by their lengths. So basically you normalize it. And usually the problem is in this part. But if you look on data, you will see that it appears to be 0 every time when the same customer, when there was no customers who interact with both items. So in a SQL way of writing things, you can just run it as one join based on user's ID and filter, so you will get it. And then just count amount of customers that interact with both products, with both items. After it, all you need to do is to define by length of those vectors. And length of vector for implicit feedback is just amount of square root of the account. That would be it. Works pretty good when we do a prediction. We do again simple matrix multiplication. In this case, with replacement of SQL. So we take all books customer interact with. Then we for each book we add a rating with similarity we compute for all other assortment, and we aggregate it. And again, we compute weighted rate, nothing more than that. Let's go to practice. This is just a showcase. And we see, first of all, it works. Second, we see increase in inefficiency. Not too big, but we still have it. And we see significant decrease of response time, which is important for practice. If you want to go further, you can pre-compute those recommendations for each particular user. And last but not least is ILS recommender. So again, we have pretty standard setup where we process and initialize matrices. Then we have loops for a certain amount of iterations, where we first set one matrix as a constant, then we set another matrix as a constant, and we train it this iteratively. And probably predict rating as for each item as multiplication of vectors for users and items. So basically, we get as outcome of this method, we get embeddings of that encode our users and our customers and their behavior in a short numerical way. Okay. If we scroll further, we'll see that this is test. Here's it. Because of sparsity, this works not so good, this specific method. But usually, ILS decomposition is what this is your golden bullet to get information about customers and products. But as it matrix multiplication, it works really fast. This is the most, perhaps the most optimized, especially because of neural networks that are pretty popular right now. Do you have any questions about these two methods? No? Okay. Then let's return back to our schema. And look a bit. Do you see browser right now?
Yep.
Okay. Let me just
No, still this code. No, nothing.
Okay, let me just share my screen in this way, then you will definitely see what I see. Is it again noisy schema there?
Yeah, it works now.
Okay, great. The thing I want also to show you is that these three basic methods could go pretty far from just simple implementation. Let's take as a starting point our decomposition, master decomposition. So we have these things. We have metrics, we have items, and we can think about it as about a system that estimate rates. So it fills gaps in metrics. We take top n items, and we're happy. But also we can do it differently. We have factors for items, but they are vectors in a certain numerical space. In this, what is important for us, they are in the same numerical space as between each other. So we can not only compute exact values, but we can compute also similarities between items. So again, we can take a sign between vector E and vector G. And we can go from it to filtering technique. We can take factors for customers, and we can use it, for example, for clustering. Why? Again, this is vectors that encode behavior of customers in our numerical, in certain numerical space. What is more important, in the same numerical space. We can go there. So, and we can use it for clustering, or we can use it again, it has similarities for our user-based collaborative filtering. We can take, for example, we can build map out of it. So if we have a certain numerical space, we can represent it as a map and give to people to visualize. To build visualization for our dataset based on behavior, which could help us for manual analysis of items, etc., etc. So, if you take standard filtering techniques, it's not only about setting distance between items. You can also go beyond it and set distances between attributes of those items. For example, how likely that authors of that people who read a certain author would read another one, etc., etc. So it's basically limited only by your imagination, and you can change these basic methods in any way you want. Just simple example we'll talk a bit later. If you think about recommenders and interaction with sorry, repeat please.
Probably some noise from the background.
Okay, that's fine. So you can also think about items that customer interact with not as something constant, but as about time series. And when you have, so you will have a set of items with which it looks horrible. Let me just tell it. So you can think about as a time series, and you can apply methods of time series prediction for it. And then you will, you will have some challenges from decoding it, but it's possible. So you will foresee what next customer would like to interact with. And again, that will be a design of your recommender system. If we'll try to formalize a bit how recommenders look like, we will end with some kind of this flow. You have several steps. So first of all, you try to take your data and encode it as in any algorithm to make it numerical. And the only difference for recommender system that you pretty often would work with implicit and explicit feedbacks. You can take it as a goal, so you can take prediction of the rating as your prime target, or you can take it as intermediate step and say that you will take attributes of your model and reuse further to, for example, to rank items. So it's not only about rating, prediction rating, it's also about how you order things. Because in the end, it's not important if you predict rating of a customer right. If you your goal will be to find items that he will like the most from all your assortment. And that's why there are two blocks of how you can evaluate those. First of all, it is feedback prediction require pretty standard things for evaluation. So this is Ernest-Year, Maya, and Laplace. So nothing new for you here. You can take it as just common prediction. So, but much more interesting is ranking. And if you think about this problem as problem of ranking things, you'll find that first such interesting measures as pairwise loss, where idea is that you compare not your predictions, but you compare your predictions with real feedback of a customer. And if customer interact with it, you should rank it higher. Or you, as we saw in a code, we estimate all list of things that a recommender gives. What also an option. So you might try to remember those formulas, but the most important thing is just to understand the difference that if you build your system to predict feedbacks, you will predict those feedbacks. But on practice, no one will actually cares if your system gives what is the difference between predicted value and real value, until the order of your recommender is correct or it is optimal. And we earlier spoke about feedback loop. There is pretty simple way how to avoid it and how to fix it in practice, and that is sampling. This mechanism is might be counterintuitive, and it will definitely decrease the your target KPI, your loss, your likelihood and evaluation values. The trick is that you might want, using rating you and ranking you designed, take a random sum sample using those rates as a weight. In this way, you will increase amount of items you recommend. So you not recommend only from top. You will also have certain chance to recommend from the bottom. And also that would basically help you to avoid these kind of biases where you feedback loop, where you get data only about products you recommend, and you recommend only products where you have data. Do you have any questions about this schema? No? Okay. Then let's move to things that is nice to know, but commonly ignored. It's several extra KPIs, let it call it this way, or extra properties of recommender system, but which usually nice to have. So first of all, it is coverage. We might want to measure what % of our assortment we recommend. not for one single user, but for all users. And we compute it pretty in a simple way. We take amount of items we recommended, we divide by amount of items. More we get, better it is. Novelty is already a bit trickier, and to compute it, we should go to a field of information entropy. And here we compute, basically, first of all, we compute a chance that this item would be recommended, or perhaps you would like to chance that this item would be viewed. And then we estimate a novelty for each particular customer for a set. So the best scenario would be if we recommend items that are not likely to be viewed. But again, you should remember that those items has less data, and mostly well, we are biased doing that. The next one, diversity. How different? What is the difference between things we recommend for the same customer? Here we need embeddings for our products. It might the same we discussed in the similarity model. So basically, we say that we want to recommend items to cover as many fields of interest of the customer as it possible. How to measure it? Compute similarity between items and say that the less this value is, the better it is. And last but not least is serendipity. This word was ranked like one of the most hard to translate. Basically, there is no way to translate it to Ukrainian. But idea is that serendipity is a property of recommender system to recommend something new that customer would like. So something unexpected, but that perfectly fit his tastes. And to measure it, we can do it in a pretty dummy way. We take a chance that we recommend by our model. We subtract chance that we'll recommend by some other simpler model, and we multiply it by reaction of customer. So basically, the only way right now to measure this property is to check a difference between two models. Nice to know that this has value, but not really commonly used. Do you have any questions about these four things? No? Okay. Then I have only one small thing left, and that is modern architecture of recommender system. For each of those, we would need a separate lecture. So I just want you to know that these approaches exist and give you a broad framework how to understand it. So factorization machine idea is pretty dummy. We take each case of interaction of customer and item. So it will be our row. We have vector that represents users there, and this is lone vectors of 0 with only one. The same vector for customers, and vectors for that describe metadata and circumstances. And we have rate that we need to predict. Forming this data set, we will apply a regression model, and that would be it. It looks simple, but so far one of the best methods are based basically on this approach. So you put all your data in one frame, you reduce, apply dimensionality reduction, and you solve it as a system. So you predict this rating. The other thing that also might you might like is transformers, and here this approach we already mentioned before, where we look on behavior of customers as a sequential process. So we have interactions of customers with items, we have next product he will interact with, and we have certain features that describe environment, so that describe where we are now. So we have embedding layer, where we convert it to numerical format, and for items we can use decomposition, for example, technique, matrix decomposition, and then we are applying we're building a neural network on top of it to predict a certain rate. Advantages that we are looking on a process as sequential process. Disadvantages that commonly it is slower. From my experience, we build it only once, and it works for us as good as our collaborative filtering model on that moment. So we decide that it's too expensive. That's shortly about it. And that is basically it. This is all I plan to talk with you today. So please ask questions.
I have a question, sort of broad one. The YouTube Music, they have the best like algorithm recommendation music algorithm I have ever seen anywhere. So my question is, does it the basis or the backbone of this algorithm consist of the method you introduced here? So
most algorithms use elements of these elements, but I don't really know. I never saw a description of their algorithms, so I can't say for sure which architecture they selected. So okay. Yes, what they definitely do, they use customer interactions, and if they use customer interactions, they use certain decomposition techniques. They try to foresee a next video, and they use it as a sequential process. So most probably they use elements of transformers, perhaps not. They don't take into account all history; they take only some. I read an article from Google which told that they use a video summarization. So they use as descriptor of video, they convert it to some numerical format. Basically, there are a lot of algorithms that create text out of video. Not subtitles, but description of video. And if you have, so it's easy to convert it to embedding, like sense embedding. So most probably they use that also. But again, this is just a guess, as I never read description about the algorithm.
Okay, thanks. Okay, well, I meant not only just YouTube, I meant YouTube Music exactly, because I think YouTube Music has even the better the algorithm they propose to try to predict. So generally, each music I listen every day, the recommendation is very, very impressive. It like just aligns with everything I listen to and all my tastes, and it's like it knows what actually I want to listen to.
Okay. Well,
very impressive.
Yeah, well, most probably again they encode it in that way, not using video, but using genres, using using basically they
metadata.
Yeah, so they use the same principles just on a higher level, because they have really broad department who work on it. So, but without exact paper, I can't say what they do.
Okay, thanks.
Any other questions?
Well, maybe I have a question then if everyone else is silent. So like every recommendation system is a kind of a trade-off between being like conservative and propose only thing that people would like with high probability, like with high confidence. And another side of this trade-off is being more into exploration, so proposing some new things to the customers. Like we are not very confident whether they would like it, but there is still a chance. So which mathematical instruments like lever for this do we have in your proposed models? How can we control mathematically this thing?
You mean how we can control, if I understood right, you're asking about how we can control novelty of our recommendation algorithm.
Yeah, kind of.
This is fully depend on a design. So you in all recommendation algorithms, basically you have data you take as a background, and then you try to predict. So you might to predict next item customer interact with, and then you will work with it as with sequential data. You might want to no, I went wrong way. What I can say that when you use the data already exists, you will also be in a certain loop. If you want to go some, and like this is known problem of any machine learning on a if we have a certain range where our system works on a boundaries of those age, our range, our predictions would be really poor. And one of methods, and I would say one of main methods to go to add some novelty is sampling. So you add to your recommendations items with lower rating than top in a top list with a certain probability. So how would it look like on practice, for example, with music? Some of things you would never heard before, but you might like it worse. So it will give you information about those domains. To really control it on a level of algorithm, well, I can give an example how we did it for similarity. Basically, we took we took several items customer interact with. We recommend as similar to the last item he bought, and which basically the formula was that rate is based on item on last item minus rate on item minus 2. So basically what we did, we took things as similar to last item as it possible to interact with, and as different from his previous interactions as it possible. That would also increase novelty just by spreading his attention. Any other exact mathematical constructions? Well, I think most common would be to add similarity rate as a negative factor there to your model.
Yeah, thank you.
Did I answer a question?
Yeah, sure. Thank you.
Okay. Yeah, you're welcome. Thanks for a question. It was interesting. Any other things to discuss? No? Okay, then thanks a lot for your attention. I have one question. I can share this slide and code if you need it. So, do you need it?
Yeah, sure. It would be more handy.
Okay, then I'll commit it to
Так,
GitHub.
давайте, дякую.
Sorry, I hadn't heard the last comment. No? Okay.
Ну, так, і приєднався теж, що
Good.
презентацією.
Okay, great. Then thanks a lot for being here. It was a pleasure to talk. If you have any questions, feel free to contact me. I'll and hope to see you in the future.
Thanks a lot for you too.
Thank
Hope
you.
to see other lectures from you.
Okay, well, we'll discuss what is interesting later then.
Okay, thank you.
Have a nice day.
Yeah. Have a nice day. Bye.